Hello friends, welcome to this video, and in this video we are going to implement the Vanilla GAN using the TensorFlow. For this video we will be using an phase dataset. So let's get started. So we'll start with the basic definition of GAN. Generative Adversarial Network or GANs were introduced in 2014 by Ian Goodfellow and his team as an unsupervised machine learning approach for generative modeling. So GAN are made up of two neural networks called generator neural network and a discriminator neural network. The generator network learns to generate new example, while the discriminator network tries to classify examples as real or fake. These two networks compete with each other to generate new samples that look like real one. Now let's move on to the coding part of this video. We will first start by taking a look at the dataset itself. The name of the folder is anime faces and it contains about 21.5k images. Now here you can take a look at a few samples after the complete dataset, and if you can see, all these images are of size 64 by 64 and they are RGB, and all these images are PNG images. Now let's move on to our file, and we'll start by importing all the libraries and the function which we require. So our main library here is the TensorFlow, and rest of the functions from all the different libraries we'll use for the completion of this task. So now we'll define some constants, and these are image height, image width, and the number of channel in the images. Now we'll define some helper functions. So our first function would be called create dir. So we will use this function to create folders if they do not exist. Okay. Next we have another function called load image. So this function take an image path and give you the normalized image. So first of all we read the image path, then we decode the PNG image, then we convert the image to float 32. Now we normalize the image in the range of -1 and +1. We normalize the image to -1 to +1 while training a GAN, as it helps to stabilize and accelerate convergence by ensuring balance gradient and prevent mode collapse. Okay, this is all about load image function. Now we'll have another function called TF dataset, and in that this function would help with training. So this is to have the training pipeline, the training dataset pipeline. So this function take all the images path in the form of a list, then a batch size as an integer value. So first of all, what we'll do, we take the tf.data API, and from there we have function called from tensor slices, and we give it the list of images path. After that we shuffle that list, and then we use our load underscore image function to read all the images parallelly. Okay, and then we generate batches. After that we have this prefetch function. So what this prefetch function does is, let's say your batch number 1 is in training. So this function, what it would do, it would keep some batches in advance. Okay, so that your training pipeline is optimized. So this is about the tf underscore dataset function. Now we'll move on to our core part of this video, that is GAN. So we'll first of all we'll build our generator neural network. So name of the function is build underscore generator, and it take an integer value called latent dimension. That is, what are the dimension of our noise. So in a GAN we take noise as an input, okay, and we generate a fake output. So this fake output can be an image, can be text, or can be anything, okay, depending upon your task. So as we are working with a simple GAN, that is Vanilla GAN, So for this we will use dense layer. Okay, and here you can see we have used 4 dense layer, and after each dense layer we are using leaky ReLU as an activation function. So now one more question you can ask is, why leaky ReLU activation function instead of normally used ReLU? So one problem with ReLU is of dead neurons. Some of the values of the feature became 0, and that causes problem in the GAN. So we replace the normal ReLU activation function with its with a leaky ReLU. And here you can see first we have noise which is given to the dense layer as an input. Okay, dense layer is followed by leaky ReLU. So we have this sequence, and within this sequence we increase the number of features. Okay, first we have 256, then we have 1024, then we have 4096. Okay, and the fourth dense layer we have number of feature equals to image height multiply image width multiply image channel. We specified these things, these image dimension, because in the layer 5 we going to reshape it so that we have a proper image that we can see, and the output of this reshape layer is followed by the 10H activation function. So 10H activation function convert any value in the range of -1 and +1, which is same as our normalized image. Okay, so this is our generator neural network. Now we will move on to the discriminator neural network. So our discriminator neural network would take an image in normal image. Okay, then in the layer number 1 we flatten it. Then again in the discriminator neural network also we will use dense layer, and here also we have 4 dense layer, and each dense layer is followed by a leaky ReLU, and then it is followed by a dropout. So we have used a dropout to make sure that the model learns efficiently. It has better feature representation so that it can classify whether the given image is real or fake. So at last, if you see, the number of feature in the last dense layer is 1, because it is a binary classification task, that is image is real or fake, 0 or 1. And we have our discriminator neural network. Now the main function is the training. I'll copy paste the code instead of writing it down. Writing would makes the video lengthy, and I explain line by line. So first of all, name of the function train underscore step. So this entire function is basically a single epoch. Okay, and it gives you the discriminator loss and the generator loss. So it take real images, then latent dimension, generator, model, discriminator, and then optimizer for generator and the discriminator. First of all, we will have the batch size. What is the batch size here? Okay, because every computation in the deep learning or in both TensorFlow, PyTorch, so every other library is done in batches. So first of all, we need to have the batch size. So we have this batch size here. Then we define the loss function. So here we would use binary cross entropy as the loss function. So in a training process, we would first train the discriminator, and then we will train our generator. Okay. So we begin with the discriminator. So first of all, we will have our noise. So if you remember, generator neural network first takes noise as an input and give you a fake image. Okay, so in our training process, while training the discriminator, we would first have our noise, then we would generate a fake image using the generator. We give it the noise, and in this process we are also training the generator, and using both. Now we have both the generated image or the fake image and the real image. So we will have the real output and the fake output when we give both these images to discriminator. Now we'll calculate their loss. So for calculating the loss, we need ground truth. Okay, so for real output, our ground truth value would be 1. Okay, because discriminator is a classification architecture basically. And for fake output, we have our ground truth as 0. Okay, for discriminator, this is the process. Real output, ground truth value would be 1, fake output, ground truth value would be 0. And if you see, we have this function in both discriminator real loss and discriminator fake loss, as you can see, tf dot once like. So in this once like, we give this tensor. So what it does, it would create another tensor of exactly same dimension, but that tensor would contain all values as 1, and same goes with the tf dot 0. Here it would again create an exact same tensor, but all values would be 0. So in this way we get loss for both the real output and the fake output, and then we join, we will have a sum of these loss which would make the discriminator loss. Then we calculate the gradient and apply those gradient. This is how we train the gradient. And if you see, I have a loop. Okay, so we repeat this process 2 times. So if we say we generate a discriminator 2 times and a generator 1 time, because the thing is that, let's say we train both of them equally. So what happened, our generator would automatically generate images, okay, and then give it to the discriminator. If the discriminator is not powerful enough that it would not be able to discriminate between real and fake, so the training would stop, okay. And in this way the generator would not be able to generate good images. So we need to give, so our discriminator need to be efficient enough so that it can really discriminate between both the real and fake. So we make sure that we train it 2 times more than the generator. Now we'll move on to the training part of generator. So first of all, we generate fake images using the generator and the noise which we have defined above. Now we have fake output. How we have fake output? We give these generated images to the discriminator and we generate fake output. Now we calculate the generated loss. So what do? We have fake output, and then here what we say, tf dot once like as fake output. So the ground truth for this fake output in the generator would be 1. Now we have generator loss. So we calculate the gradient and apply those gradient, and this is the training step, and it would return discriminator loss and generator loss. Next, we would have a function called save float. So what this function does, it save all the images as a square. Let's say we have 100 images, so it would convert them to 10 by 10, 10 rows, 10 columns. Now we'll move on to the main function from where the execution start. Okay, so first of all, we will define some hyperparameters. First is the batch size. In my case, I am setting it to 128 because the size of the image is small and my GPU is RTX 3090 and it has 24 GB memory, so it can handle a batch of 128, and you need to set it according to your GPU memory and other system configuration. And the later dimension is 64. You can increase it accordingly. Number of epoch 1000. Then the number of sample, basically how many images we would generate. Let's say we are training our GAN, so we want to see after each epoch how the generated sample look. So we'll generate 100 sample, that is a 10 by 10 square. Next, we need to load all our images. So our dataset folder name is anim folder, okay, and then we'll print number of images. So let us run this file, that is gan.py, and you can see we have near about 21.5k images. Next, we would use our create dir function to create 2 folders, and these 2 folders are samples in which our generated images would be saved, which are generated during the training. And next is a saved model. In this folder, we would save the weight file of both generator and the discriminator. Now we would build our generator model and the discriminator model. Let's run the file again and see the summary of both of them. So first we have, here is the generator. It takes noise and give you the fake image. Second is the discriminator. It take both. It can be fake image or real image and generate the and predict whether it would be a real image or fake image. Let's move on to the next part of the code. In the next part, we will define the optimizer for both discriminator and the generator. So we would have separate optimizer for both. Here you can see both of them have same parameter, but still we would have separate optimizers. Next, we would have two more line of code. Here we would have the images data set. So this function is basically used to create the training data pipeline. Next, we have the seed, or you can say the noise. This noise we're going to give as input in each training epoch, and we generate the fake images and we save those fake images. Okay, so here size would be n sample, that is 100, and latent dimension equals to 64. Size is 100 by 64. Now we'll begin with the training. Okay, so we have a loop for number of epoch time. So these are the number of iterations. For each iteration, first of all, we'll start the time. Then we have two variable which will store the loss. Okay, for the entire batch. Now we would have another for loop, and in this for loop we have image dataset, and it will give you a batch of images, and we give those batch of images to this training step, and other values we give it, and it would give you discriminator batch loss and generator batch loss, and we would sum those values into these two variable, that is d loss and g loss. After that, we would find the mean discriminator loss and mean generator loss. Then we would save the weight for both our generator model and the discriminator model. Now we would use the seed, that is the noise, initial noise, and generate some fake images, and we save those fake images. We again calculate how much time is taken for each epoch, and we print the values. Now let me run the entire code again, and we'll see epoch by epoch. You can see some messages from TensorFlow. Okay, so first epoch is done. If you see here, this is the first epoch. You can see epoch 1 by 1000. It took nearly 8 seconds. This is discriminator loss, then generator. And okay, some messages are there. Just ignore. I also ignore those messages. You can see fifth epoch is done. Now let me train it to few epochs, and here you can see both the folders. So first, let me check saved model. You can see we are saving both our generator and the discriminator model. Later we will use the generator model. Okay, next we will have samples folder. In this folder, it would save the generated images. You can see within first epoch only, we can see that this is a face, it has eyes, it has hairy structure. Okay, and if we go with next generated sample, it's improving. Okay, and we have trained it till 16. Okay, let me stop it now. So in my system, it's not taking that much time. So within, I think, one hour of training is enough for this process. You can see that the difference between the images generated at epoch 1 and epoch 17. So it's improving. Now what I'll do, I'll delete both this folder and replace them with mine, because I've already trained this model. Now I'll show you samples. So this is images generated on epoch 1, and this is on epoch 106. You can see there's a drastic improvement in both of them. Now what we'll do, we'll write another set of code to generate these images. So first of all, we'll have our libraries. This time we need few libraries. Again, we have that save plot function which we have used in our GAN file. Here again same, nearly same. Now we'll write our main function from where the execution begins. So first of all, we will load our generator model. We will have a number of samples. So this should be basically a square of integer. So it can be like 10 by 10 because it would generate images in a square. Latent dimension 64. So this value should be same as your training value, what you have specified during training. Next, we would have latent point, or you can say the noise. Then we give that latent point or noise to the model and it predicts samples and we save those samples. And every time it would save image with the name fake samples.png. So let me run this code. It should test. Okay, so it is run and we have this fake image. Okay, so you can see now at least we can say it's generating some samples. Let me run this code again and you would see the image would change. You can see now image is changed. Okay, now let us compare this with the real images. So how much difference is there? So you can see the difference is there, we can say, because we are working with a basic GAN, that is vanilla GAN. So it is not one of the best GAN, it is one of the basic GAN because we are starting with the GAN. Okay, so but for a starting GAN, these images which it is generating is good enough. Okay, so that's all for the implementation of simple GAN. I hope I make everything easy for you and you have learned something from this video. And if you enjoyed the content or anything from this channel, please make sure to subscribe the channel for more such videos. And thank you. So in future, let me tell you, I'll bring a video on DC GAN also, which is an improvement over this. So let me show you how the examples of this DC GAN would look. Now here are the fake examples generated by DC GAN. Now you can see the improvement when you compare the images generated by the normal GAN and the DC GAN. So that's all for this video. Thank you. Have a nice day.